That must go there. And that goes there. Yeah, that does. Gulliver's laws. That must go there. And that does. That must go there.
Royal Institution Christmas Lectures. Lecture 6, Beyond the Map.
It's appropriate to begin by reintroducing our famous star Beatrice the mouse to make a small point. One of the keen mouse observers in an earlier audience pointed out to us that he was in some doubt about Beatrice's weight, and we checked it. Now I must tell you that the real point of science is not to get it right the first time. The real point is to know how to find and correct errors, and we were able to do that, and we found that Beatrice does not in fact, as we wrongly reported, weigh 13 grams. She weighs the splendid sturdy weight of 35 grams. And therefore, she does not eat rather more than half her weight, which remember puzzled us a little bit each day. She eats a little less than 1/5 of her weight each day, which makes her fall closer to the curve that we expect for many animals. She eats about 1/5 her weight each day. You eat about 1/32 or so of your weight each day, at least the boy we tried out did. And the great guard's horse ate about 1/60 of his weight each day. So you see, as we said, the fraction of your own weight that you eat each day gets smaller and smaller the larger the animal becomes. The weight goes like W, but the food goes only like about W to the 0.7, and that's the fraction therefore goes down as you become bigger. It was very nice to learn that, and Beatrice indeed fits the curve. Thank you, Beatrice. I'm glad we reweighed you. A second point, some people have tried to make the legato machine work by drawing letters looking for words. That's good fun to try, and I hope you will try it. I can give you a little help. If you want a letters pool for the legato machine, for an English recipe, you should take the mixture of letters there indicated. If you just take the 26 letters equally numerous, you'll get words, but most of the words you get will be quite unpronounceable, full of consonants like X's and Z's and J's and so on, and very hard to pronounce, more suitable for some tongues than for the English. So since we speak English, we have adjusted the letters so they come out pretty pronounceable, though not very meaningful, and in the legato machine. So that may help a few experimenters. Finally, I'd like to introduce today's lecture, this time not by referring to Swift and Gulliver, not by picking up a copy of Gulliver, since we are beyond the range of Gulliver's voyages today. We are going to discuss those parts of physics, of modern science, which go beyond the easy experience of the world, and I think you will find it a strange and exciting voyage. But I cannot refrain from calling to your attention two books both by English authors, beautifully done, both men writing in the last decade or two, who have written very well on scaling and its importance in the physical world. A small essay in the book Possible Worlds by J.B.S. Haldane, who died in the last year, and a whole chapter in a splendid book called Growth and Form by Darcy Thompson. Both of these chapters are very worth reading, not very difficult, and they comprise a great deal of what we have said in these lectures. Moreover, you can obtain these works either by getting the original books from your libraries, or on the paperback shelves. I'm sure you can find a book called The World of Mathematics, in which the chapters I'm referring to have been excerpted, along with much other good reading. So, something to go back to if you want to know more. Now, if we will consider the problem of the day, we want to discuss going beyond the physics that we have had so far to try to find some of those new bits of modern physics which carry us very far indeed, from the style of classical times. But I want to do this with the aid, let me say, of one device, as though I were taking a ship. It is, of course, not a ship, but it is one single kind of device which occurs in the world many, many times, over and over again, in all sorts of connections, with all sorts of shapes and sizes and purposes. And by looking at this one device, I think I can show what the physicist has found in his voyages well beyond the map. Now, you may recognize what these objects are. You see a spring with a weight on it, another spring with a weight, a piece of elastic band with a weight, a pendulum, a couple of other springs. I'm going to call them all by the rather ugly but still nice technical term, oscillator. All of these are oscillators. And of course there are many more kinds of oscillators in the world, and we will show you some of them and talk a little bit about how they work. The oscillator comes in many forms, and physicists can recognize in nearly all of them certain common properties, certain qualities in common. Let me talk a little bit about a few of them, and you will see what I mean. And of course, those of you who've studied some physics will be quite familiar with this account. Let me look first at the pendulum. Now, if you look at any of the other oscillators here, except for the two pendulums, you will see really two essential parts: an elastic band or a spring, and the mass or weight that is on the end of it. Here the supporting string, while an essential part, does not change at all. I can't stretch it at all under this load. It's just a stiff string. It doesn't change its length. There is nothing springy about the pendulum. And yet, when I let the pendulum go, it comes back. What is the spring that is pulling the pendulum bob back to the center? Anybody? Go ahead.
Inertia.
That's interesting. Inertia, I think, would make it keep on going. Why would it go back to the center? If it started out this way, inertia would alone keep it going the same way, would it not?
Gravity.
Gravity. And gravity is the pull of what? It's not a word that makes it go up and down. It's a thing. What is that thing? Yes?
Pull of the earth.
It is the earth. The earth is the missing spring, just as you say, gravity we call it. But I'd like you to think of it as a physical thing. It's part of the pendulum. Without the earth, the pendulum would not work very well. On the moon, the pendulum worked quite differently from what it does on earth. So gravity, provided by the earth, provides the spring, the second part of the pendulum. I'd like to show you one more difference between the pendulum and the other oscillators, and I think this difference is easy to see. Notice this oscillator going up there in a kind of ragtime rhythm, rather fast. Let me put another mass on it, loading it down more heavily. Of course, it stretches to accommodate the mass, but then it will oscillate again anew about a new position, no change. But notice, what would you say about the rhythm? Slower, isn't it? More stately, perhaps waltz time now. And I could keep on going. But if I try this pendulum, you see its rhythm, and this one matches it pretty well. And if I put a heavy load on this, much heavier than the one that is there already, I don't think it will very much change the rhythm. Let's try it. Maybe do a little because it's hanging a little farther down than the main ball, but it's pretty close, yes? Yet I loaded it with a much heavier bob than was on there to begin with. So the pendulum somehow doesn't show the effects of putting more mass on, and indeed we can check that very carefully, and it does not. How can that be? After all, putting more mass on must have more inertia, must be harder to move. But what about the spring that moves it, which is the pull of the earth? What happens when we put more mass on? The spring pulls harder, yes? The earth pulls more, and the two go in perfect step, and therefore the time to go to and fro, which we will call the period, because the motion is periodic. One trip is exactly like the next trip, and exactly like the next trip, with very small differences. So we'll call the period of the pendulum that time it takes to go back and forth. And the period of these gravitational ones, where the spring is missing and is invisible, so to speak, or is all around us, beneath us, does not depend on the mass, whereas here the period definitely depends on the mass of the pendulum. Let us look a little farther at a couple of other examples which may be interesting. Here we have some vibrators, oscillators, which I put here most particularly to show that you don't have to have them oscillating vertically. The vertical condition has no role to play. These oscillate very nicely horizontally, as you can see, and now they're pretty well tuned. Every musician knows how hard it is to tune two things precisely, and you will see these are not exactly in step, but they're pretty close. Now, the spring and the mass together determine the period of the oscillator, and that is true for all sorts of oscillators. The key point which allows me to call an oscillator a simple oscillator is shown perhaps in this way. This one has a kind of droopy motion, but I'm going to let it die down just a little bit. A simple oscillator has the remarkable property that its period does not depend upon the amount by which it is vibrating. Now, real oscillators, such as we will see in a moment, all the kinds of oscillators surround us in the world are very often not quite simple oscillators. Physicists can study those too, but it's more difficult. He prefers to study the simple oscillator, and that's what I should be talking about. No real oscillator is exactly right for it, but they come pretty close. For example, these are pretty nearly in tune, and I've allowed this one to die down to rather a small amplitude. I can wait a little bit, it'll die down even farther. Then if I start this one again with its big amplitude, the two will still remain in step pretty well, even though this one is going at a rather smaller motion back and forth, and this one going at a much larger one, which means that at least for these small displacements, there's not much difference in period, depending on what I shall call the amount of the swing, the excursion in the swing. And that is the test for a simple oscillator. So if we remember that the period of the simple oscillator does not depend upon the amount, I will say period independent of what I will call A, the amount of swing. And that is nearly true for many real oscillators, and it is what the physicist means by a simple oscillator. And of course, if I made it move only a millimeter, which is too small to show in the audience and in the television screen, then it will work very beautifully as a simple oscillator. It works very closely indeed to the ideal case, but it's not much fun to look at. So you must imagine we're always talking about small excursions, small amounts of trip in the case of the oscillators. Now let's look at a few other real oscillators. Here's a not unfamiliar one, I think. He's oscillating too with a little bit of complexity. And here a familiar sort of rocking pan. And here one which is electrically fed. But all of these are oscillators, and if I make them go through only very small excursions, then they become simple. That's to say, then the time it takes does not depend on the amount of the excursion. With these, it isn't quite so. This is a display card sort of motor. Just for fun, you can see what he looks like. We have another kind of device which I would like to call I should like to use the word perhaps, he's a pseudo-oscillator. Notice the excellent on-off flashing of this familiar object, like the Metropolitan Police cars. But it's not really speaking an oscillator in our sense at all. It's not going to and fro. You can see how it works, perhaps. It's a bit bright, but if I take it out, you can see the mirror is spinning. And so first the beam in one direction, then another. This is a rotator, not properly speaking an oscillator at all. Those of you who like the mathematics of physics will know that there is a very close relationship between the rotator and the vibrator, but we will speak mostly of vibrators now, and we'll put this one in only to show that sometimes there are rotating objects that appear to oscillate. Oscillators of mechanical kind are most familiar. In fact, here we have this model of probably the most commonplace man-made oscillator in the world, the balance wheel of your wristwatch. This, of course, is a very large example and a beautifully made old one. We put a couple of paper flags on so you can see it spin. And this wheel going to and fro on its bearings, driven by this spring, is, of course, the timekeeper, the steady oscillator inside the ordinary wristwatch. This mechanism is only to drive it and to allow it to move allow the driving gear to move the hands. Of course, real oscillators lose energy as they go, and therefore they won't go forever in general unless you keep feeding energy into them. Now, what we need to inquire is how to describe this vast variety of oscillators in some reasonable way. Let me go back again to my wigwag, because I rather like it. It wags along very nicely, and if I wish to change its period, I can put on some additional mass. And now it will go in a sedate fashion, much more slowly. And indeed, if I put the mass in a particular place, another place rather, it will again be affected. I can take the mass off. But it hasn't anything like as much effect in here as it has out there. Let us try to talk a little bit about the mechanics, the theory of an oscillator, of a simple oscillator. I shall make a few statements which are, I think, quite easy to believe, but of course to prove them we take either careful measurements or a genuine mathematical deduction. And it's holiday time, and I should not like to make a serious one. But I would like to remind you of the ideas, and if you want the proofs, you can look them up or work them out as you choose. The most important part of my discussion will be based on two ideas which I hope you will remember something about. Let us look at this oscillator. I let it go. It's standing still now. I let it go. When it comes back to the original position each time, I assert that it's not moving at the instant when it stops going in this direction and starts coming back again. At that very moment, it must have gone to zero speed, because it can't go from plus speed to minus speed without going through zero. If then it has zero speed in this position, you know that the kinetic energy depends upon the speed in the familiar form. Ke for kinetic energy is proportional to the mass times the square of the speed, v, and therefore there must be no kinetic energy at that point. Yet there's some energy, because pretty soon, watch it, as it goes through the center of its motion, it's moving quite fast. And then it slows down again, speeds up again, back and forth. The play between the inertia and the force of the spring is what, of course, makes it move. Now, if it has no kinetic energy there, and we admit that it hasn't, and quite a lot there, where did it get it from? It must get energy from somewhere, and that energy must have been in the system in another form. And of course, the energy which is there is the energy which arises whenever you distort or bend or change the shape of any solid substance. Elastic energy, we call it, it's a special case of what we call potential energy, and I think that's the best word for it. The gravitational pendulum has the same idea. It has more energy when you raise it up. So it has potential energy as well. And the potential energy doesn't depend at all on the mass, because it doesn't know how much mass it has, so to speak, when it's bent. It's not moving at all. It has the potential energy right then and there. Mass doesn't affect it. Just the amount of energy stored in the distorted position of its spring. And so that is proportional to the amount by which the spring is bent out of shape. And in the simple pendulum, it always goes like the square. In fact, this is I don't need the constant if I say proportional. This is the great result. We call it a simple oscillator when the kinetic energy has this simple square dependence and the potential energy has the same sort of square dependence. And this, algebraically, is what is responsible for the result that I gave that said the period does not depend upon the amount of disturbance, the degree of the trip. And that, in fact, is going to be enough to define all that we need to say about pendulums. Because what I need to talk about now is the period, P, and the mass, M. There is, of course, another quantity, that's the spring. The description of the spring has to be put in. But if you will recall, there really, if I have a description of the spring, for example, like this, Then the kinetic energy turns the potential turns the kinetic. Their maximum values must be equal if there are no losses. And we neglect loss for the, you know how many swings it goes when I have a good oscillator. That means the loss per time is very small. I will forget that we don't need to discuss it. And that suggests that these two must have maximum values which are the same. Otherwise, how could it get enough energy to go back and forth through the central position to the outside, center, outside, each time making this complete transfer? Whenever it makes that transfer, it doesn't lose except a little bit to the outside world. 1% or less. It will go hundreds of times. Therefore, if these two are equal, the velocity, however, the maximum velocity must depend on the amount it moves divided by the period. So if I put that in here, then a squared comes here, and a squared comes here, and we see that the amplitude enters both of these forms the same way. Therefore, it does not really determine the ratio of these two quantities. Their equality is independent of the amplitude of this amount of disturbance, which I call A, or amplitude. And there must be a relation between them, therefore. So there's a relation between the period, K, and M. And if there's one relation among those three numbers, only two of them are enough to describe the pendulum. So if I give you a period and a mass, then you needn't know what the spring is doing. The spring must have just enough potential energy so that at the right excursion, it takes up all the kinetic energy and gives it back again. So we can describe every one of these oscillators without talking about its details, but just its overall behavior. We can describe each one by giving two numbers. The period, let us say in seconds, that it takes to go to and fro. And the mass, let us say in grams, which is the mass of the bob. And what I want to do, my Gulliver voyage, my super Gulliver voyage I want to discuss today, is in fact the study of all possible oscillators. That is to say, of all possible pairs of numbers, P for period and M for mass, considering a very wide range, much wider than the difference between Lilliputians and giants, or the difference between hummingbirds and VC-10s, a much wider range than that. So wide a range that man-made equipment will of course not suffice. We must consider atoms and electrons and the depths of space in order to get these numbers going. But remember, we shall describe them always by thinking of the period of the oscillator and the mass that is doing the oscillating. And if the oscillator is simple, that is enough to describe how it will work, and I shall simply say no more about this algebra, but take it that you believe that we can describe every oscillator by giving its period and its mass. And we'll discuss those as time goes on. Now, we have oscillators, even man-made oscillators, in a very large range of scales. I'd like to show in a film a famous man-made oscillator, which began as a simple oscillator, but soon made such great excursions, that trouble occurred. This is a bridge in Tacoma, in the state of Washington, the United States. About 30 years ago, or a little less, this bridge, under the influence of the wind, began to oscillate very severely. And after a while, you'll see what happens. Look at that splendid oscillation. It takes many seconds for a period, does it not? Possibly 5 or 10. And what do you think is the mass of that oscillator? Is it measured easily? It's not just a few grams. That's a whole bridge roadway. It must have weighed 1,000 tons. So that's a very large oscillator indeed. And you see what happened. The oscillations were fed by the wind. Their energy grew and grew and grew until the distortion was so great that it could no longer restore itself, and the bridge fell apart. Fortunately, no one was hurt in that accident. The bridge had given signs of bad behavior, and all it did was cost a great pile of money to build another bridge across the river. On the other hand, we also have small man-made oscillators, and to show an interesting one, I have here a nice sample. Here is a small tuning fork. I can hear it, and possibly you can hear a recording of what it sounds like. Works very well. It's quite a small fork. I can show it here. And Bill, I think we get a better look at it if you were to magnify it for us. Thank you very much. Bill will put it close to the lens of the camera, and we can all see in the screen the peculiar shape of this interesting little tuning fork, which must weigh a matter of a gram or a fraction of a gram. And now this tuning fork has been used in a watch, just as the balance wheel was used in watches for hundreds of years. So this one for a few years has been used. We're now setting up a watch in a glass movement. There you see in the same position as the tuning fork alone, you see the tuning fork mounted in its watch. Those two cup-like structures at the top of the screen are magnetic. They are moved back and forth by the magnetic forces. The rest of the gear work and the little bit of electronics in the watch is what drives the fork and what translates the to and fro motions of the fork into round and round motions of the hands of the watch. Such a complete watch looks like this. It's a very handsome watch indeed. It's rather nice because it is exactly the sort of watch which is taken by astronauts as their main timekeeper in voyages in orbit. It would be nice to have such a watch. We have big tuning forks too, not as big as bridges to be sure, but pretty good sized. This is a fine old tuning fork of the era of Professor Tyndall here at the Royal Institution. A tuning fork just like the one we saw. This is steel, the other was stainless steel, the one in the watch, which keeps better time. And this one makes a very low tone, almost so low that I can't hear it. Possibly you can hear that. And it's driven electrically very much like the one in the watch. Just to show there are various kinds of oscillators. Now we have other oscillators which are so fast in motion that we don't see them, but we can hear them, and there are oscillators moving, and generally if they're not blown too hard or struck too hard, they are simple oscillators as well. Can we have our musicians to work these air oscillators, all parts of which are invisible? Get ready and give us a tune. Thank you very much. A beautiful harmony on this excellent instrument. That oscillator consists of a perfectly static bottle, nothing moving about the bottle, but you can study and learn that there is a springy volume of air. The volume of air in the bottle has pressure, resists being compressed. If you push down by increasing the pressure in the neck, it resists, and so pushes up again. That's the spring. What is the mass? The mass is the air itself in the neck of the bottle. And the two together work back and forth. If I excite it by feeding energy in with the puffs of the breath, I can make it oscillate a particular tone determined by the size and a little bit by the shape of the bottle. And of course, you have all sorts of musical devices, all of which are oscillators. For example, this excellent musical device, and I think we have a musician who's going to give us a splendid rendition on the one-note bass fiddle. Again, notice the string vibrating. I think you can see the flag blurring a little. Very good. Thank you very much. It's a delightful tune on one string. Let me call to your attention. In a sense, we could of course have put that paper flag at any point on the string. At nearly all points on the string, that flag would move back and forth. So there would be an oscillator. In a sense, a string is a set of tiny oscillators all working together, each point of the string being a simple oscillator. And those of you who studied the theory of strings will recognize how familiar this point is. Well, now let me discuss the possible situation of using oscillators as a springboard to the recesses of the atom and the depths of space. It doesn't sound as though we should be able to take such a commonplace thing as a simple oscillator and move it over all that range of scale, but I think we can. And I'd like to ask a very curious question. I hope you will see that this question sounds very easy, and then if we start to look at it closely, we see that, like many questions in science, it is by no means easy at all. The question I would like to ask is, we understand the mechanics of an oscillator pretty well. If we feed no energy into it, it takes on no energy. It will stay in its position of rest, what we call equilibrium, right in the middle. That's obvious. Now let me ask the question, can we really take oscillators, very big ones and very little ones, and keep them absolutely at rest? That's the question I'm going to ask. And now let me go step by step through the efforts that one would make if he tried to do that, to show you how really difficult it is and what surprising results come if you try this trick. Let us look at one sort of oscillator, which already shows the experience of men in measuring things for hundreds of years by the way it is made. Such a balance, a standard chemical balance, familiar thing, has been used even by the alchemists 300 years ago or more. And they early found that it was very valuable to fit such an instrument, which is a sensitive oscillator. At the moment it's clamped Let me stop that pan, which is reflecting too much the disturbance being placed on the table. At the moment the balance is clamped, that's to say it's taken off its sensitive bearings so it can be carried around without damage. And I will put it on its bearings, and now it is quite a sensitive oscillator, which would tremble gently as you put weights in different sides and give you good measurements. Why is it in a glass case? You will understand when you see me operating it without a glass case, as one might have done in the old days. Goodness, that sample weighed a lot. Of course, that would be no way to weigh anything, and you would be a little suspicious of the chemist who sold you materials after he blew heavily on the pans. No good at all. And that is the first sign of why it is difficult to keep, say, small oscillators standing still. You must first isolate them from all external forces, outside disturbances, which might make them move even though you're trying to keep it still. So we put it in the glass case against air currents. Is that enough? Not quite, because with no air currents at all, this is evidently not very good for the balance either, and it's beginning to swing, and I would not trust the weights that I was getting if somebody kept hitting the corner of the table that way. It would be a very poor way to run an analytical laboratory. And this, of course, is real, and the more sensitive the balance, the more difficult it is to shield against those disturbances. Those disturbances are everywhere, even if we are very quiet and walk on tiptoes. Not all London is walking on tiptoes. And even if all London we would do our experiments at 4 o'clock in the morning and everybody in London is asleep, still the waves are beating on the shore, and the earthquakes are beginning to send their vibrations through the earth, and we will always have some trembling. So we must do our best to get rid of that. But we can get rid of that by heroic effort. Here's the kind of effort we would have to use. For example, we have these rubber shock mounts, and we put a heavy plate on top of them, and this oscillator would then be a very well-defined, slow oscillator, and most of the trembling of the outside world would no longer affect some instrument that was placed on that fine shock-mounted slab. So it looks pretty good. It looks as if, were we to place our apparatus in a glass case and keep it away from all vibrations and work out in the countryside and stop the lorry traffic and do all those things, we could finally get an oscillator that didn't tremble at all. Here is what such an oscillator might look like, a really very sensitive one, so sensitive that we're not really able to run it at its full under these circumstances. It's clamped for motion, and it has a scale and a light source. The light source will shine on a mirror, a very delicate mirror, hung in a very delicate wire, which trembles back and forth. It's meant for measuring electrical currents, so we can notice a very small current which deflects the coil only a small amount. I think we see something. Very good. Now then, if we could reduce the lights, I think we should see how such a galvanometer works. You notice the spot on the scale. I can see it from close up quite well. There it is. It's right here on the scale. I don't yet see it on the there we see it. Very good. And notice also that it is constantly trembling. That's just the case of the galvanometer. You see the spot is constantly trembling. There's the light spot, and it will never be a vibrator quite at rest. Now, you may think that if we isolated it completely from all disturbances, and notice when disturbances come in so we can take care of that, that then we would be free of the trembling. But this was done, and the result I can show as follows in the transparency. It's too hard to show here. There's really too much disturbance to mask it. What is there beside the galvanometer mirror inside the galvanometer case? There is, of course, air. The air molecules are in ceaseless motion. The mirror of the galvanometer then makes Brownian motion, lights down I think, makes Brownian motion exactly as the paint pigment did in the other day, and that Brownian motion shows up as a constant trembling to and fro of the galvanometer mirror. Here is a recording, a photographic recording made some years ago in a laboratory showing this irregular motion, just as though we were to plot a Brownian motion particle's position. It would go up and down in irregular fashion. So that the Brownian motion is the cause of trembling. We cannot get rid of that. The only way to eliminate that would be to cool the whole thing off. It depends on the temperature. If we make the whole thing colder, the trembling is less, the molecules move less rapidly, so we can get rid of that, we would think, in time. You may ask, Suppose I take out the air molecules. I can do that pretty well. For example, I can evacuate the whole case, and then there's no air. Still, the mirror itself and the suspension thread itself are made of molecules. They internally vibrate with temperature motion, and so even when there is no air, you still get vibrations. Their shape is different because they now tend to vibrate always at the resonant frequency, always the tuned frequency of the mirror, but the vibrations are still random. It goes for a while, then it starts up again in a different way, and goes for a while, and again in a different way. I would like to have darkness for this, please. And here's the curve you get in this proposition. You see here it is vibrating, then it starts over again and vibrates again. It looks different from this, but in fact, the mean disturbance, the average disturbance here, is exactly the same as the average disturbance here. Removing the air makes no difference to the amount of disturbance, only to the shape. Now, lights, please. We can see this also in electric apparatus. We've already seen it, and I think we can also hear it. There is television snow, the video noise, and audio amplifier noise. Those again are, so to speak, electrical analogs of Brownian motion, and demonstrate once again to us that you can't get rid of the trembling motion just because of the internal temperature of everything that we have. So one cause of incessant motion is the motion of molecules and atoms. But you see how remarkable that is, because we've discovered, so to speak, the nature, the atomic nature of everything in the world by studying the trembling of a single oscillator. We'll say more about that. Suppose that is not the only, suppose we understand that cause. For example, we might cool off everything and reduce that to very little effect. Is there any other kind of trembling which might occur? And here I will show you a kind of trembling in a very large oscillator indeed. I'm sure you've all seen and heard of this effect, but perhaps it can be made a little, it will seem a little strange anyhow. This is an official record of the tide curve at Margate, east of London on the North Sea. Notice the swelling and rising of the tide through the days. These are the weeks just before Christmas, from the 13th of December to the 20th of December. Each day there was a rise and fall of the tide, and as you went through the week, the curves slide across because, of course, the tide shifts with the position of moon and sun about an hour each day. So you see this, and you see the regular increase as the moon and the sun pull either with each other or against each other. You see the tides tend to have a bigger excursion at some part of the month than at others. Here is a still later record of the tide, the response of the great oscillator, the sea, to the distant gravitational pull of moon and sun, which I think you understand quite well, in a rough way at least. It's a complicated problem at any given port. And here we see it again. I like this curve particularly well because this curve shows also that even the tide measuring instruments, which are very sturdy instruments, exposed as they must be to the open sea, are quite subject to external disturbances, just as our balance was, just as we had to put shock mounts. You see this thickened line and this difficult region here where the curve is not very smooth anymore? Those are times when a northeast wind was blowing hard on the shore at Margate, and even the best protected instrument will feel the racking forces of the wind. Those are not regular tremblings, but they are tremblings nevertheless, and they have to be taken into account if you were to calculate just what is to be due to the moon and the sun. Now the remarkable part of it is, you may say, well, the ocean is a great oscillator, yes, but it's so unusual and so unlike my springs and masses that we can't put it in the same box. And I agree with you, it is really too complicated. I only gave you that to suggest it. But I say that we can take an oscillator very carefully made with the right value of period and mass, and I will show you which value later on, bring that little oscillator into this room, or in fact this room is too difficult because it shakes too much. But we brought it and we held it there yesterday in a basement room in this very building, and there in the basement room on a concrete pier, without any access to the sky at all, by watching the trembling of the little oscillator, we could detect the presence of the sun and the moon by their effects on an oscillator which responded to the pull of gravity, the differential pulls of gravity and the relative motions of these objects. Think how marvelous that is. Could we see the gravimeter? Think how marvelous that is. You could do astronomy if we had never seen the sky, if we had perpetual cloud. We could still do astronomy once we were clever enough to study very carefully the tiny motions of the right sort of simple oscillator. Here it is. It's a beautiful device. You've been traveling with it, Bill. I see it has a Bermuda stamp on it. It's lent to us very kindly by Imperial College Geophysics Department It's a very valuable instrument, and it travels all around the world by air, measuring these effects at various parts of the Earth. I lift it out. It's just a portable instrument. Of course, it's clamped now. Were it not clamped, I would not be able to touch it. It must be able to stand this motion. And in the eyepiece, one can read the reading when it's unclamped, which is something we don't want to do in this particular circumstance. And we have read it the other day, as I say, yesterday and this morning, and we got the following results, I think extremely interesting, showing that, so to speak, the effect of gravity is always present from the other bodies of the solar system. And of course, in principle, if we had good enough instruments, we could detect even more distant objects. Here's what we saw. This curve drawn there, this is the maximum distance of deflection. This is Wednesday midnight, Wednesday noon, midnight between Wednesday and Thursday. This is just this noon, and here we are now at this time. This curve shows the expected reading of the instrument. Now, we couldn't stay up all night and read it every half hour or so, which would be very nice to do. We just weren't energetic enough to do that. And therefore, we read it a few times to see how it agreed with the curve, and I think it was tolerably good. There's a point, there's a point, there's a point, and there's a point, and there was a pretty good agreement. And if you watched that and had a recording device especially, you would clearly make out this tide-like motion in the little instrument inside this case, which is nothing but a very delicate balance beam with a spring so adjusted it has an extremely slow period of response. It weighs about 50 grams, has a very slow period of response, perhaps 100,000 or a million seconds is its period. So very delicate is the spring. And that is enough to show what I would like to call the trembling motion, this steady, which cannot be gotten rid of no matter what you do. There is no place you can hide where such an instrument will not, once you remove all the other disturbances, still show this trembling. Of course, it shows the temperature trembling as well, but it's designed to make the temperature trembling small and the gravitational tidal trembling large. And you can adjust the sizes of oscillators in this way then to pursue all the kinds of motion in the universe. So put this fellow away. I understand it costs about 5,000 pounds to make such a delicate instrument. It's really quite a fine device. Here is another. No, I think we'll just let that curve go, Bill. I think we've seen it enough. We had, in case we didn't get a good reading here, we had a curve taken in Texas some time ago where this instrument was made, but let's stick to the London curve, which is more fun. Now, let me look at another kind of motion which is quite surprising. This is motion which is neither due to temperature, nor due to the effect of remote gravitational bodies, but due to the inner nature of the particles of matter themselves, what we call the quantum effects, the quantized motion of the electrons within the atom, of atoms within a molecule, and of the vibrations internal to a crystal. We see these effects in the large scale sometimes, but they're very hard to recognize. For example, this bouncing repulsion of the magnets is in a certain sense due entirely to the persistent motion, to the permanent trembling, actually a kind of rotary motion, of the electrons within the atoms of iron of which these magnets are composed. Without those motions, we could not have such magnetic effects. I can show you that because I can make these motions very well, the same kind of magnetic effects very well, without using iron at all. That's to say, without using an iron plate. This is not iron, but aluminum. I took the same magnet, nothing happens, where a magnet will stick very nicely to the switch box. On the other hand, if I am to make the currents which will repel this, as the currents in one magnet repel those of the one below it, I can do that, but I have to ask Bill Coates' help to bring on a lot of energy in this fine, thick cable. So I will turn it on, and you will see the plate rise. It certainly is rising. You may be able to see the gap. If you can't, I shall put the paper underneath it. Certainly floating in the air, but it doesn't do that permanently. It does that because I force it to make currents with this great degree of electric power, and once I've made the currents rapidly dissipate, so I must make them over and over and over again. In consequence, the whole thing gradually warms up, and I don't have a permanent magnet effect at all, but an electromagnetic effect with a lot of loss accompanying it. But the marvelous thing is that we can nowadays, and we here will be able to do so because of the aid of our good friends at the Clarendon Lab in Oxford, we'll be able to show you a persistent current which could last, say, 100,000 years without detectable losses if we had that long to wait. And in a sense, we can make a permanent magnet, not by depending on the atoms of iron, but entirely without iron, making a permanent electromagnet. We can turn off the current, it will still remain a magnet. Turn off the external current. It would last forever. But it is not magnetized at all. It is simply the current running around. I can prove that because we can then take away the current and use the magnetic energy to do some electrical work. And then it's back down again, an empty electromagnet, no current, no magnetism, just a coil of wire. To do that wonderful thing, though, we must reduce the whole system to very low temperatures so that the noise, the Brownian noise, does not disturb the delicate persistent currents which can be set up at very low temperatures. And now I think Mr. Hudson and Bill, let us try to see what this device looks like. Thank you. This is the Dewar flask, a strong aluminum flask with vacuated double walls, which preserves within it a sample of liquid helium at very low temperature. Now, in order to control the flow of current in this electromagnet, which is inside here, we're not allowed to reach in or to have leads that go in that have losses. We must arrange to be able to do everything inside the cold. So, hold it for a moment. We do this by using that control to open or close a superconducting part of the circuit so we can feed current in from the outside without short-circuiting it out. We can do that by heating, very cleverly, heating some small part of the circuit inside. It makes it stop being a perfect conductor. Persistent currents do not flow in it. And then we have this magnetic coil, which you'll see later, which is inside here. And now we can excite it from the outside, just as we did before. But now we have batteries to feed current in. And very slowly, this electromagnet will become energized by the currents that flow in it. And it will become a magnet. You saw it draw the iron spanner, and it repeatedly does so. And this magnet would last, if we were able to keep it cold, indefinitely. As I say, a measure of 100,000 years before any detectable change would occur. The current is flowing in there forever. Now, if we can short-circuit out the outside current, which has losses, we can keep the current flowing forever. Can we do that?
Not just yet, we're just looking at the inductive voltage.
Right. We have to be careful about this because a lot of energy is stored in this, and its rate of change is quite important. If it changes too rapidly, we could damage equipment. The superconducting current, the quantum current, is flowing in this metal.
Almost, huh?
And eventually, we'll be able to have a complete current wholly in the cold. And when the current is wholly in cold, then the current will flow indefinitely.
Just turned off the heater now.
Turned off the heater. Now then the superconducting short circuit will appear to get rid of the effect of the batteries and make the current flow entirely inside the flask. That takes a little time for the part of the circuit to cool down. Notice it's still a good magnet, of course. It has plenty of current flowing in it.
Taking a while to cool.
Mm-hmm. I hope that battery's all right. What we're trying to do is, without moving any parts, try to make a switch work inside here by drawing a superconducting wire across the coil.
Now we'll move the current to 0.
And now the current from the outside is 0. Would you turn off the switch, Peter? Thank you. Now to make sure that there's no current, notice it's still a good electromagnet. There's no current coming from the battery, clip the battery leads in case anyone doubts us. Still a very good magnet. This is a persistent current, and it would last, if we could afford to keep it in liquid helium, for a very long time indeed. This is the kind of current that is flowing around inside the atom itself, owing to it has been made on a large scale. And now to show that the power is there, it's not a permanent magnet, we can take the power out, dumping the energy to raise a weight, a heavy brass weight here, and to burn lights, using up all magnetic energy. Then the electromagnet will no longer be a magnet, no current, no iron, and this will fall away.
Okay. You
must take some... This is a more sensitive test. You see the lights are still there. A little bit of energy is still leaking out of this fine stored magnetic coil. And then at last all will go and the spanner will fall away and we'll have no more magnet.
So it's still decaying.
Still decaying. We can still see it on the voltmeter. There's a little bit of current left. It's pouring out all its energy into the load, and when it's lost all the persistent current, it falls away. So we have made a permanent magnet and unmade it. Thank you very much. Great work. And now, if we're lucky and these hard-working people do not have much trouble, we may be able to see the insides of that thing, and you may be a little surprised. Think a little bit, but don't tell anyone what you expect to see, because you remember what's inside that dewar is about 3 degrees above absolute zero in temperature. Only at those low temperatures can we avoid the disturbances of the temperature motion, which makes the Brownian motion that would have spoiled the persistence of the current. So open up the dewar flask and reveal what is inside, to show what is inside. What is inside, of course, is a specially made electromagnet, which is a coil of metal, actually a niobium titanium alloy, a very unusual and specially made alloy, which acts as a coil of zero resistance when it is cold. And of course, when it's at room temperature, it has an ordinary resistance like any other metal. But this is what we can do if we can make the ordered motion, which is characteristic of the atomic currents that permanently flow inside the atoms of iron, and which we can ingeniously, as these people have ingeniously done, make flow inside large man-made circuits, provided only we can keep the thing. There you see, it's really cold. The condensation, thank you very much, the condensing vapors of this moist air are coming out in frost on the coil. And there it is, thank you. Just the leads, the little switch, very cold indeed, and I can feel the cold air pouring off it as it comes down. This is all that there is there. It's really only a coil of wire, nothing else. But mind you, when it was working, there was no loss. We didn't prove that, but the fact that we recovered all the energy and cut off the battery leads showed there was not much loss. And if we measured it quantitatively, you would see that there was absolutely negligible loss, a very, very modest amount of loss indeed over a very long time, which of course is not at all the case with that kind of a device, but is very like this device, because this device, the currents are flowing within the atoms themselves, all lined up together. And here the current is flowing around a man-made orbit, if you like, the orbit which is the coil of wire that makes up this cold electromagnet. And that is quite a remarkable result. Thank you. I think we'll look at the board and then see where we've been on our voyage. Oh, thank you. Now what I have done here is make a map of the voyage beyond the map, which is a little bit of a strange phrase, but that's how it fell out to me. Here I have put a graph which covers a tremendous range, not like 12-fold large in Brobdingnag and 12-fold small in Lilliput, but a huge range. Look at the range. This is the period of an oscillator, from 10 to the 10th seconds to 1 second, to 10 to the minus 10th seconds, to 10 to the minus 20 seconds. And here is the mass of an oscillator. From 1 gram to 10 to the 10th grams, and this way to 10 to the minus 10th, 10 to the minus 20th, and 10 to the minus 30th grams. Notice the enormous size of those exponents. Don't try to count one by one from 1 to 10 to the 10th. Life is too short. And every point on this graph then represents some kind of a simple oscillator with a definite period, because I can go over here and read off the period, and a definite mass, I can go up here and read off the mass. So every oscillator that we can imagine, every simple oscillator, must be somewhere on that graph. Let us see where the oscillators live that we have really seen before us. Here at this point is the Tacoma Bridge. Here at this point is the little delicate beam of the gravimeter. Here at this point is the tuning fork in the watch. This patch area here is the kind of apparatus that men can normally make and display in an engineering way in the laboratory. Just in that patch. The rest of this curve, the rest of this plane, we probably will never be able to produce in the laboratory by man-made equipment. It is too delicate, or too huge, or too fast, or it has something that we can't quite reach. Maybe someday we can, but for the moment we don't know how. Now, in the domain marked temperature, the trembling motion, which every oscillator must have, no oscillator can be without some trembling motion, here the temperature motion, the Brownian motion, is dominant in this huge part of the plane. Notice, the smallest the most sensitive man-made equipment, like the galvanometers, does show some Brownian trembling. In this marked temperature, for the temperature motion. In this domain marked gravity, for the tidal motions, the gravitational forces of the distant bodies determine most of the trembling. And you see, if almost all the man-made things, except the most sensitive ones, would be limited by this. If you look at very low frequencies up here, if of course you go down to high frequencies, you don't find it. Below this line, way down at very fast oscillators, 10 to the minus 13, 14, 15 seconds. That's like the oscillator of an electron in an atom. And all the way across, everything faster than that, the trembling motion is determined neither by temperature, nor by gravitational effects, but by quantum effects. The complete change of mechanics to the mechanics of the quantum, not known to Newton, which has been the contribution of this century to understanding the physics of the very small. And I've drawn the lines. At every line, the two effects are equal. So here, for example, temperature and quantum effects are equal for the trembling of an oscillator. Here, gravity and temperature are equal. And well away from the lines, the dominant is the one that's drawn there. Here, for example, all three kinds of trembling meet and are equal. Such an oscillator, I calculate, would be a thing like a small minor planet, maybe 100 miles in diameter, vibrating back and forth as fast as a molecule in the crystal. Now, we don't know how to make such a device or even to dream of such a device, but that's what you would have if you would have all of these three equal. So you see the kind of domain into which we can voyage by looking at the properties of a simple thing like a simple oscillator. It's interesting to ask, where do atoms come on this chart? Well, of course, their electrons are 10 to the minus 27th grams, and the frequencies are in here, so atoms, of course, come about in here. Molecules come in here. And that's why quantum theory and some degree of the theory of thermodynamics, of thermal effects, is necessary for discussing the spectroscopy of atoms, just because of their place, reviewed as oscillators on this diagram. So in this way, we can cover every kind of oscillator, oscillators from Tacoma Bridge, from the wild notions of planets moving as fast as molecules, down to the very particles of the atoms themselves. The position of these lines, of course, depends on the circumstances. I have done this for room temperature. If I use lower temperature, then I push the temperature motion away. There's much less temperature trembling, and the quantum effect dominates more easily. That's why at low temperatures you can study quantum phenomena even in the large scale, because this line has gone up, and I can therefore go to bigger masses and still see the quantum effects. The gravitational line, of course, depends on the position of the Earth, the orbit of the Earth, the Sun, Moon, and so on. If I calculate for all parts of the solar system, this line doesn't move very much. You can imagine going way out into space, far from any stars, then this line would move down, and temperature motion would be important for still other objects. It would be much harder to find objects controlled by gravity. But these lines don't move very much, and since we don't have every part of our environment at our disposal, probably we will never be able to do much more than jiggle a little bit these conditions. The wonderful story of low temperature physics, which the Clarendon Laboratory has so nicely demonstrated for us, lies in the ability to change this margin a little bit. That then is the story of Gulliver. I've come to the end of my time and the end of 6 lectures. There is much more to be said, but it is you who have to say it, because I do not know what the future is going to bring. I am quite sure that other maps will be made by other voyagers which will be as strange and as wonderful to us as the voyage of Gulliver and the map of the oscillator have been in the past. Thank you very much.
Yes.